Hi, I'm NASA Skate Dude Will.
Today we're going to talk about the physics of roller skating.
But first, gotta be safe.
Alright, let's go!
Hey NASA Skate fans, I'm excited to share some fun examples of physics while roller skating. We're going to talk about Newton's laws of motion, gravity and friction, and conservation of energy. We're also going to have a fun at-home activity at the end to learn about surface friction. At the end of the video, we hope you'll have a better idea of how physics help you have an awesome day at the skate park. Newton's first law of motion is defined as an object at rest remains at rest, and an object in motion remains at motion at constant speed and in a straight line unless acted on by an unbalanced force. Take this skate, for example. It's just sitting here doing nothing. It isn't until someone gives it a push that it starts to roll. Now, it's not going to roll forever, right? It's either going to run into something like that rail or slow down on its own. In both these cases, however, an unbalanced force is present. When skaters roll to a stop, it is friction that slows them down and acts as the unbalanced force described in Newton's first law. To get moving again, the skaters require another unbalanced force. Take Will and I. When we were introducing ourselves, we were at rest. We moved forward by pushing off the ground with our toe stops and thus applied the unbalanced force to the skates, which moved us forward. This is an example of Newton's first law of motion. Now, things don't always roll down in a straight direction, and we don't always roll on flat ground. Today, we're going to have a little fun at the skate park where we have ramps, half pipes, and quarter pipes to help keep things going. And we're going to be moving with the help of three forces. Gravity, a force which pulls us down half pipes. Friction, a force that slows us down. And finally, our skater force, a force that we produce using our muscles and stored energy. Gravity is the force by which a planet or other body draws objects towards its center. Earth's gravity is what keeps you on the ground instead of floating off into space, and it's what makes things fall. The force of gravity is what keeps all the planets in orbit around the sun. Anything that has mass has gravity, and objects with more mass have more gravity. Gravity also gets weaker with distance, so the closer objects are to each other, the stronger their gravitational pull is. Gravity is what holds the Earth in orbit around the sun, and what keeps the moon in orbit around the Earth. Earth's gravity comes from all its mass. All its mass makes a combined gravitational pull on all the mass on your body. That's what gives you weight. So why do skaters care about gravity? Well, as Will is showing us, it makes dropping into a half pipe super fun. We were wondering, what would happen if Will dropped in on planet Mars, a planet with less mass than Earth?
3, 2, 1.
Because gravity is weaker on Mars, Will weighs less than he would on Earth. If we could put the same half pipe on Mars and have Will drop in, we'd see him go a lot slower down the ramp. This is because the gravitational pull that's pulling his mass down the ramp is weaker, and his body's experiencing less weight force that would want to pull him down towards the center of Mars. Friction is resistance to relative motion between two surfaces in contact, and this resistance is what causes a slowing of motion. Skaters will eventually come to a stop on flat ground because of the friction acting in the opposite direction of their motion. In skating, two surfaces that experience friction resistance are the wheel surface and ground surface. In addition to wheels, skates have something called a toe stop, a little rubber part on the front of the skate designed to help skaters slow down. Friction resistance can occur on various surfaces, including these ramps which are at an incline. While we use our wheels to go fast, we use our toe stops to slow down and even stop. There are three different types of friction that occur between solid surfaces: static, rolling, and sliding friction. Static friction is present when objects are resting on a surface. In addition to using toe stops to slow down or stop, skaters can use them to push off. The static friction between the toe stop and the ground allows the skater to push off instead of slip away. This is similar to what your shoes do when you walk outside. If it wasn't for static friction, your shoes would slip out every time you tried to walk. The toe stops have enough friction to help us walk up the ramps and even stay in one place. Here's an example of me standing still on a ramp. My weight force due to gravity is acting in the downward direction. And because this ramp has a slope, there's also a normal force pushing back against my body weight. These two forces combine into a resulting weight force, which wants to pull me down the ramp. Friction, like gravity, has a force associated with it. If the resulting force is not larger than the static friction force, then I'm not going anywhere. If these arrows seem confusing, think of it this way. My weight wants to pull me down the ramp, but there's enough static friction fighting against it so I don't go anywhere. Sliding friction is a type of friction that occurs when an object slides on a surface. Sometimes we use our toe stops to safely slide down ramps. Most of the time, sliding friction is weaker than static friction. Take this example of me earlier standing on the ramp. Before, the resulting weight force that wanted to pull me down the ramp wasn't strong enough to overcome the static friction holding me up. But if I slightly shift my weight back just enough, I can overcome the static friction and start sliding. Once I'm sliding, the force pulling me down the ramp is still larger than the sliding friction force, but I'm still slowing down more than I would if I was rolling. Let's look at how sliding and rolling down a ramp look side by side. Rolling down is much faster because a different type of friction is present. Wheels and anything that rolls experience rolling friction. Rolling friction acts on objects when they are rolling over a surface. Rolling friction is what causes ground objects, such as balls and roller skate wheels, to slow down and eventually stop. Do you remember that skate at the beginning of the video and how it's not going to roll forever? If nothing is in its way, it will slow down and stop on its own, and that's because of the rolling friction force that acts opposite the direction of motion of the skate. Rolling friction is much weaker than sliding or static friction, which means the object will take longer to slow down. This is why wheels are so popular on skateboards, cars, and bikes, and skates. And that's it. Those are the 3 types of friction experienced between solid surfaces: sliding friction, static friction, and rolling friction.
Wow, that was so much fun. What do you want to do next?
I don't know. Wait, are those our friends?
Oh yeah, it's NASA Sk8rnauts, Jess and Laura.
Hey guys, how's it going? It's great. We're just talking about the physics of roller skating.
Do you guys want to join?
Yeah.
Let's go.
Liftoff. We have a liftoff.
The definition for Newton's second law is that the acceleration of an object depends on the mass of the object and the amount of force applied. In other words, the force experienced by the object can be calculated by multiplying its mass times its acceleration. Newton's second law also defines force to be equal to the change in momentum of an object over change in time, with momentum being calculated by multiplying an object's mass times its velocity. Objects with more mass have more momentum, and they require more force to stop. Think about it. Would it be harder to stop an elephant coming at you or a mouse? Look at this example of Jess giving Laura a little push. Here, Jess is applying a force to Laura who has mass. The acceleration of Laura is her change in velocity over a period of time, in this case the time between Jess pushing her and the time of this image. An object with higher mass will require more force to accelerate at the same rate as an object with less mass. So Laura's going to put her big backpack on, and Jess is going to give her the same push. See how she doesn't go as far this time? That's because even though Jess is applying the same force, Laura has more mass now, so her acceleration is going to be less at the time of the push. So what happens when mass changes but acceleration stays the same? We tried to test this by having Laura drop down the quarter pipe with and without the backpack. Because her mass is larger with the backpack on, but her acceleration is the same as when she didn't have the backpack on, Newton's second law tells us that the force required to stop her would be larger with the backpack on. You can also say that she has more momentum with the backpack on because objects with more mass have more momentum than objects with less mass that are going at the same speed. Newton's third law of motion states that whenever one object exerts a force on another object, the second object exerts an equal and opposite force on the first. Let's look at Laura for an example of this. If she exerts a force on the ramp exerts an equal and opposite force on her, so she rolls away from the ramp. If you've ever pushed yourself off of anything, such as the side of the pool, you've proven Newton's third law.
Hey NASA Skate dude, Zack.
Hey Niki, what's up?
Ready to do some more roller skating physics?
Let's do it.
All right, let's go.
Zack and I will push off of each other to demonstrate Newton's third law. Watch as we exert force towards each other, but both move backwards. This is due to the equal and opposite forces where our hands meet, pushing us back. Now we'll try tossing a bag back and forth, which causes us to roll away from each other. Believe it or not, the bag is exerting a force pushing us back as we throw it away from ourselves. If you don't believe us, check out Zack throwing the bag by himself. If you look at his feet, he rolls back in the opposite direction of where he throws the bag. So the bag is pushing on him just as hard as he pushes on it. The law of conservation of energy states that in some problem domain, the amount of energy remains constant and energy is neither created nor destroyed. Energy can be converted from one form to another, but the total energy within the domain remains fixed. Take this roller skate as an example. At the top of the ramp, the roller skate has potential energy, a stored form of energy that can produce motion. The potential energy is calculated with the object's weight, which is calculated from mass, and height. When the roller skate is in motion, the energy becomes kinetic energy. The kinetic energy is calculated using the object's mass and velocity. Because this energy is finite and energy cannot be created, the skate will not go over to the other side if both sides of the halfpipe are the same. Conservation of energy applies to skaters dropping in as well. Watch as my potential energy gets transferred to kinetic energy, then back to potential energy when I reach the other side. Like the skate, I will not get higher than where I started if I simply drop in. However, skaters can do something called pumping. By bending our legs, we are able to stay at the same height. But because energy can't be created or destroyed, where is this additional energy coming from? Well, it's coming from us, the skater. Humans produce their own energy from the healthy foods we eat, so we're able to pump our body to maintain the same height and even get out of the halfpipe. Let's look at another skater, Laura, who's going to drop into another halfpipe. At the top of the halfpipe, Laura has maximum potential energy and her velocity is 0 because she has no kinetic energy. Once she drops in, her potential energy starts converting into kinetic energy and she starts to pick up some velocity. When she's at the bottom of the halfpipe, all her energy is converted to kinetic energy. This is where she has the most speed. After this, she starts to lose speed as kinetic energy gets converted to potential energy. She will continue this cycle from potential energy to kinetic energy to potential energy until she eventually slows down to a stop due to friction. Throughout this cycle, small portions of her energy are being converted to heat thanks to friction, which result in Laura losing energy over time. Let's see if conservation of energy is affected by mass by putting Laura's big backpack back on. Now she's going to drop into the halfpipe again. Is she going any faster now that she has the backpack on and has more mass? Remember, potential energy is calculated with mass and height, while kinetic energy is calculated with mass and velocity. The answer is she'll go at the same speed. Even though she has more potential energy with the backpack on, that energy gets converted to more kinetic energy when she's rolling on the ramp. Since her mass is not changing as she rolls and energy is converted, the speed in her kinetic energy can be related directly to the height at which she started at, which is the same in both examples. This is why in our earlier demonstration, Laura was going at the same speed at the bottom of the ramp after dropping in. We've talked about how energy cannot be created or destroyed, how energy can be converted, and how mass relates to conservation of energy. But how does the conservation of energy law apply when energy is transferred between two objects of equal mass? Watch Jess skate towards me and bump into me. When she does so, she's able to transfer her kinetic energy to me, giving me velocity I did not have before. Also notice how she comes to a stop and now she has no kinetic energy. We switched places with me as the bumper and Jess as the roller and had the same result. Because we have equal mass, the velocity of the person doing the bumping is equal to the person who rolls away after getting bumped. This is an example of conservation of energy. Another way to explain this is conservation of momentum. Because I start with no velocity and Jess ends with no velocity, the momentum Jess comes in with is the momentum I leave with. Also, because of Newton's second law, we know the change in momentum over time is equal to the force with which she bumps me with.
Man, I wish there was a way we could have this much fun at home.
Oh wait, I have an idea.
Hey everybody, I've got an idea for a cool activity we could try to learn more about the importance of surface friction when it comes to wheels. So in some of our earlier videos, we learned a little bit about friction, but why does it matter? especially when it comes to roller skating or even NASA. Well, at least with roller skating, we want to make sure that we have the right balance of friction to ensure that we have a smooth ride without slipping and sliding all over the ground. Believe it or not, NASA cares about that too. NASA engineers design vehicles that use wheels all the time. Things like airplanes, space shuttles, or even lunar and Martian rovers. And all of their wheels need to be designed to be able to ride smoothly over whatever surface they're going to be riding or landing on. Lucky for us here on Earth, we have civil engineers who've developed roads with a certain amount of surface friction that makes it easy for things like cars, buses, airplanes, bikes, and even roller skates to easily ride over them. But what happens when we can't control the kind of surface that we're working with? For instance, if we were designing a rover to ride around the surface of the Moon or Mars, we don't already have the tools there to build the nice paved roads that we have here on Earth. So today, I'm going to be enlisting your help for a special NASA engineering project. We're going to be designing the next Martian rover. In order to do this, we're going to need to run some experiments to better understand how surface friction can affect a vehicle's performance. For these experiments, we're going to need two things. The first thing you're going to need is a toy car, something that's small, is easy to move around, and has wheels. And the second thing you're going to need is a notebook in order to record all of your observations from our experiments today. We'll try rolling this vehicle across different surfaces around our homes to try and understand how the roughness or smoothness of the different surface types affect the vehicle's performance. The results of our experiments will give us some clues about how things like terrain type and surface friction will affect the performance of our vehicle on Mars. I'm going to conduct my first two experiments inside of my home. Now, you and I might have different surfaces around our home, but that's fine. Feel free to test on whatever you've got. And remember, a good engineer always takes notes, so be sure to write down all of your observations. My first test will be here on this hardwood floor in my living room. Let's give this car a push. Wow, that was a pretty smooth ride. Next, I'm going to try my second experiment on this slightly fuzzy carpet. Let's see how our rover does. That was still a pretty smooth ride, but it definitely slowed down faster than when it did on the hardwood floor. Let's go outside now and see how well our vehicle does on this rockier terrain that I found on my driveway. Let's give our car a little bit of a push. That didn't go very far. Why don't we try pushing a little bit harder? That went a little bit further, but I definitely had to push a little bit harder and put in a little bit more power to get it to go over this rocky surface. The last place that I'm going to try and test is at the street at the end of my driveway. But remember, don't go out in the street without an adult supervision. It appears to be a little bit rocky, but less so than the driveway. Let's give our car a push. That definitely went more smoothly than it did on the driveway, but still a tiny bit bumpy. Let's write this down and then go discuss everything we've seen today. Based on our observations, it seemed that our rover was able to ride over smooth surfaces much more easily than it was able to over rough and rocky surfaces, like we found outside. Now, when scientists and engineers do experiments on different terrain and surface types, sometimes they'll measure this thing called the surface friction coefficient, based on the materials that the surface is made out of. Now, we weren't able to measure it ourselves today, but we were able to observe the effects that different terrain types can have on a vehicle's performance. We know from scientific data that NASA has collected from orbiters and other rovers that the surface of Mars is pretty rocky and rough, much like my driveway, which means it's likely going to have a higher surface friction coefficient. Since we observed before that it would take a little bit of extra power or push to go across a rocky surface, that's something we're going to have to consider when it comes to designing our rover and its wheels. On my toy rover, the wheels are pretty hard and they're pretty small. Perhaps if our wheels were a little bit bigger and a little bit softer, like they are in my roller skates, they would have a much easier time going over these rough and rocky surfaces. NASA engineers have conducted experiments, just like the ones we've done today, to design durable wheels and powerful vehicles that can ride across rough surfaces with higher surface friction coefficients. This will be especially important for our rover going across the rocky terrain of Mars. Well, everybody, that's all I've got for today. Thanks for helping me with the special NASA engineering project. I hope you've learned a little bit about the importance of things like surface friction when it comes to vehicle performance. Now, let's go head back to our friends.
Hey,
Jess.
Jess.
Hi, guys.
Wow, that was a really cool experiment, Jess.
Thanks, I had a lot of fun.
Wow, high fives all around.
Woo!
Well, kids, we hope you guys had a really good time, and we hope that you learned something. Have a NASA Skate Day.
All right, guys, let's roll.
Go faster, faster, hands in the air, we're gonna crash. Searching for the answers, like Galileo, the proof is looking glass. Thirst for reason, our dreamer's eyes we gaze into a sense of purpose, know my view. Like finding water on the moon.